Hello everyone, my name is Wang. Today I would like to share some information about our reference system. And today I would like to cover the following points. First, I would like to talk about the validation of perception systems and some problems we may meet. And then I'd like to introduce our reference system, which is designed to solve these problems. I would like to introduce its details, its workflow, and some extended application of it. And finally, I will give a short introduction of our company, RoboSense. So let's start with the validation of perception systems. So for AD or ADAS systems, usually there are three parts: perception, decision, and control. Perception is the first step. And if there is anything wrong with this part, the whole system fails. And also nowadays, people are using multi-sensor fusion system. People are using LiDAR, camera, radar, ultrasonic, and so on. And the systems are becoming more and more complicated. So how can we guarantee such a complicated systems to work stable and well? Actually, we need some solid tests and validation. So from our point of view, there are two types of tests. The first one is the test of sensor hardware. For example, LiDAR. We may test the ranging accuracy, ranging resolution, intensity of this sensor. These are all about the sensor hardware. This part is very important, but we don't want to focus too much about this part. We are going to focus more on the other type of test, the test of sensor function. So actually, we not only want to obtain the raw data of the sensor, but also want to achieve some functions based on these raw data. For example, the object detection, say lane line extraction. And all these functions need to be tested. And from the development point of view, development and the test, they form a loop. Developing and test and then develop again. So actually, an efficient test can accelerate the development of the whole product. So finally, actually for the test, we need to do the real road tests. And actually nowadays, many famous autonomous driving company are doing such things. Let's say Waymo and Baidu, they have driven over millions of miles. Yeah. So tests and validation are really very important for our development. But actually, it's not very easy to perform a very good test. At least we may meet three problems. So the first problem is called the accuracy of ground truth. So the basic logic for test or validation is very simple. First, we need to get the result of the sensor under test. We call this the DOT result. And then we need a reference result. We call it the ground truth. So then we compare the difference between the ground truth and the DOT result. Then we know the performance of our sensors. So here's the first problem. How can we guarantee the accuracy of the ground truth? The ground truth actually composed of many different items. We may have some dynamic ground truth data, say the velocity of targets, the size, the position, class, ID, and so on. And also there are some static ground truth data, for example, about the lane line, the road edge, the road curve, the position of them, the curvature of them, and so on. Yeah, so how can we guarantee the accuracy of all this information? Is the first problem we meet. So the second problem we're going to meet is the efficiency problem. So let's say some information I just talked about, say the class, the position of the target. Actually, we can use manual labeling to obtain very accurate ground truth data, right? But the problem of such way is it's too slow. Let's say use the LiDAR labeling as an example. By some simple calculation, we know that actually the labeling efficiency is about 1/1000. For 1 second data, people need 1000 seconds to label them. And this costs a very long time and a large amount of money. So actually, this is not a good way. So we need a very efficient way to acquire a large amount of ground truth data. This is the second problem. So actually, these two problems are all about the acquisition of the ground truth. And after we get the ground truth data, we need to run the test. So the third problem is about the test. So actually, in the application of AD and ADAS, we may use 3 types of sensors: the camera, radar, and the LiDAR. So the working mechanism and the data structure are quite different for these 3 sensors. So when we design the test, actually we need to consider all these differences and the characters of these sensors. So I will give an example about this thing. So recently we want to test the recall rate of our perception algorithm. So if we are talking about the camera, the image perception algorithm, usually we may use IOU as a standard for the recall rate test. It's perfect. It's a very good standard. It's okay. Now what we want to test is a 3D point cloud perception algorithm. So if we still choose the bounding box IOU as a standard to test the recall rate, it's not a good choice, because right now to label the 3D object is more difficult than labeling 2D image. And B, because of the working mechanism of LiDAR, actually, for many target objects, the boundary is not very clear. So the final labeling bounding box are not very accurate. So in such situations, if we still choose the IOU of 3D bounding box, the final test result is not very reliable. So here we choose to use the IOU of points. In such a way, we get a better testing result. Yeah. So here, this example tells us that actually when we design the test case for different sensors, we need to consider the difference. We need some very customized test. So actually, these problems are very common during the test process. So we would like to design a system to assist people to avoid these problems, to assist OEM, Tier 1, and the research institutes to perform highly efficient tests and validation, and also help to accelerate the mass production of ADAS and AD applications. Okay, so this is about the first part. I just explained the goal of our product, why we want to design such a system. And now I would like to introduce some more details about this system. So actually, the reference system is composed of 2 parts, the OBU part and the server part. The OBU part is a multi-sensor fusion hardware platform, and its main function is data collection. And for the server, actually most of the data processing is done on this part. And here is a very important character of this reference system. The processing is offline, and this is not a real-time system. And I will introduce the reason of this design later. Okay, here is some features of the reference system. So first, we use a high-end and highly mature sensors to build this system. So we want to generate very accurate ground truth data. So from the sensor part, we need very high-end sensors. And then this is about the hardware part. From the software part, we use some very powerful software algorithm, and also we design this offline processing workflow. This is the most important part. And finally, for the test, we design some customized tests for different sensors. And also we have built a full stack toolchain to make it very easy to use this system. So first about the hardware part. The main sensor of this system is LiDAR. Since LiDAR can generate very accurate 3D information, so it's very suitable to be the main sensor of such a reference system. So here we use the RS Ruby LiDAR, which is a 128 channels LiDAR. And I think this is basically the best LiDAR in the market. Later I will show some road test point cloud of this LiDAR. And besides the LiDAR sensor, we also have 6 cameras in the system and 2 radar, also with a high-end RTK. So basically these are all the sensors in these systems. And most of the sensors are integrated on the roof bracket. So the advantage of this design is, first, it's very easy to mount the whole system. Second, we don't need to dig any holes on the vehicle body, so there are no damage on the car. Okay, here is a road test data of the Ruby LiDAR. So first you can see the vertical resolution is very high, 0.1 degrees. So actually we can get almost pixel level point cloud. And also we can see the intensity of this data. We can see very clear the lane line and and some markers on the ground. These are very important, and it helps a lot for the lane line detection. Okay, next we're talking about some software and the algorithm of this reference. In this system, we will use some point cloud AI perception algorithm, use some SLAM algorithm, and some multi-sensor fusion algorithm. So I believe you are very familiar with these parts, so I don't want to introduce too much about them. So I would like to talk more about this part, the offline optimization of detection and tracking. As I said, offline processing is the most important character of this system. So why we use such a offline processing workflow? So we believe there are 2 advantages of the offline processing. The first one, we call it the breaking limitation of real-time processing. And the second one is the full life cycle optimization. So the first one, breaking limitation of real-time processing. So let's use LiDAR perception as an example. So right now, most LiDARs actually their working rate is about 10 Hertz. So every 100 milliseconds, we will have a new frame of point cloud, which means we need to finish the perception algorithm within 100 milliseconds, right? And also we will have some other operations, like say the sensor fusion, or maybe later about control and decision. So actually, maybe we want to finish the LiDAR perception algorithm within, say, 50 milliseconds. And also, there are usually some limitations about the computational part. We may want to use maybe FPGA or some chips. So the computational power may not be that strong. And because of all these limitations, the final model we use, or say the perception, some logic we use, cannot be too complicated because we need to finish all of these things within 50 milliseconds. And as a result, we sacrifice the precision of the final result. However, if we do all these processing job offline, we don't have such limitations. We can use the most powerful computer to finish all this processing job. We can design, we can use very good model. We can design some more complicated logic, and we don't need to care about the 100 milliseconds limit. We can just finish everything in 200, 300, or even more, maybe 500 milliseconds or even more, right? So we can get the most accurate result we have. So this is about the first thing, to break the limitation of real-time processing. The second one, full life cycle optimization. So for real-time processing, usually we use the current frame to do all the perception job. And what's more, maybe we can use some history frames together as a sequence to do all these perception jobs. That's the most. That's what we can do. But for the offline processing, we can use the current frame, we can use the history frame. Also, we can use some future frames. Actually, we can use all the information during the life cycle of one target to finally optimize our result. This is very important. This helps a lot to improve the final performance of our algorithms. Okay, so finally about the toolchain. Actually, we designed many tools to make the whole system easy to use. We have some data collection tools, the visualization tools, manual correction, and the evaluation tools. And I will introduce some details about these tools in the later slides. Okay, so now let's move to the third part, the workflow of this reference system. Actually, there are 5 steps. So the first one is the system deployment. So we need to deploy this whole system on the test vehicle. And then the next part is the data collection. So we will run the test vehicle on the real road to collect data of our reference system and the data from the DUT. And then after the data detection, we will transfer all the collected data to the offline server. And on the server, all the data will be processed offline. Then after this step, we obtain the ground truth data, then we can run the evaluation part to get the performance of our DUT. So finally, we can feedback all this information to the R&D R&D department, and they can improve the DUT algorithm of the hardware itself. And then we do the data collection again to perform a new round of tests. Okay, then I will introduce some details about these steps. So first, the system deployment. We will send the two engineers to the field to help deploy all these sensors. And we will do the hardware deployment, the sensor calibration, the DUT adaptation, and some software deployment, and finally the training of the whole system. Okay, so after the first step, the whole systems has been mounted on the test vehicle. So now we need to run the data collection part. So actually there is a data collection tool installed on the OBU, and this software, this tool can actually achieve many different functions. It can manage all the sensors on the ground. It can split the recorded back file. It can do the visualization and so on. So here on the right side, it shows the pictures of this software. Here you can see some data. The blue points are the LiDAR points, the green dot are from the radar, and here are the camera images. So all the data collected are recorded as a raw spec. Here I would like to introduce more about this function, automatic back splitting, and this one, semantic labeling. So for this part, automatic back splitting, actually in the real test, actually we may run over 4 hours data collecting one day, and there we may collect a huge amount of data. So what we don't want to see is all the data recorded in one raw spec file, right? So here we provide a automatic back splitting function. So the software will split the raw spec based on some standard, for example, the distance, the time, or maybe the size of the back file. And also, the operator can manually split the back file with just clicking one button. Yeah. And another reason to split the bag is about this part, the semantic labeling. So actually, for a good test, we don't want not only consider the quantity of test data, we consider more about the quality of the test data. So we may consider some corner case, right? So for example, some special vehicles run over a test car, or maybe some cut-in, cut-out case. So these cases are very important, are very valuable test data for the development. So we have this semantic labeling function here for each back file. People can label it. For example, label it as a cut-in file, like cut-out or special vehicles and so on. For one back file, there can be several different labels. Yeah. So and we will provide a data management platform to manage all these data. So the operators or test operators or the R&D people can have a better use of all these test data. Okay, so after the data is collected, this data will be transferred to the offline server. Here we will do all the offline processing to generate the ground truth data. So here is a flowchart about this offline processing. Here basically we are doing 2 different jobs. The first part is the multi-sensor mapping. and the other one is the perception part, object detection, these things. So the first part, the mapping. So many people ask this question: why do you need mapping? So mapping helps about 2 points. The first is about some free space detection, lane line, and the road curve extraction. Yeah, all these operations are done based on the map. And the other part is with a good map, actually we can remove some false detection, which helps to improve the performance about the perception part. This is okay. So this is about mapping. For the perception part, actually, first we will do a deep learning perception for the initial operation. And after this part, most of the objects are detected correctly, but still there are some false negative and false positive. And then we will use some machine learning algorithms and some other rules to optimize the recall and the precision. Also during these operations, we will have some multi-object tracking. And we'll do this twice. First here, and the other part here. We do the tracking again after the optimization of the detection. We do the tracking again, and also here we fuse the radar data. And finally, we can give it optimized path of all the objects on the ground. Okay, here shows an example of the processed result. Here you can see the original point cloud. We can see the lane line, these white lines, and the road curves, and some moving targets. For the dynamic ground truth, we can generate the velocity, position, size, class, and ID of the targets. And for the static ground truth, we will generate the curvature, position of all these lane line and the road curves. Okay, so here is a demo video of the final result of the reference system. So here is the raw data. Here shows the road edge, these two green lines. Here is the ground. This part is the ground. Here is the lane line. And the moving targets on the ground. So for this system, we will detect all the objects within 200 meters. Okay, so right now we have obtained the automatic generated ground truth data, but still actually no algorithm can provide 100% accurate result. So still right now the ground truth data is not perfect. There are still a very short portion of wrong results. So the next step here is the manual correction. So we still want to correct the wrong parts of the ground truth data. Here we will provide a tool to achieve this function. Here you can see this is this tool. So the operator can easily locate the wrong detection result and to fix the detection result. Okay, so after the manual correction, actually we believe we have already obtained a good enough reference data. So the next step is to evaluate the performance of the DOT. So here on the left part, we show the basic logic of this evaluation. So first, we obtain the DOT data from the OBU, from the vehicle part. And then we obtain the ground truth, the GT data from the server. We input these two data into the evaluation module. And finally, we can get the evaluation report. So here we also provide a tool for this evaluation job, and it can do many different things. So here I would like to introduce more about these two, the synchronization and the data matching. So actually, we may use this reference system to test different sensors. And these sensors may work in different rate, right? So the first thing is to synchronize the GT data and the DOT data, right? So here we just do the interpolation of the GT data and align them with the DOT data. Okay, so then after the synchronization, the next thing is about the data matching. So right now, actually for one real target, we have two results. The first is the DOT result, and the other one is the GT result. How can we match these two? How can we know these two bounding box are actually from one target? So here we need some matching algorithm. And as I mentioned in the test problems about the third one, I said we need some customized tests. Here is what we do. We actually designed the three different strategies to match data for camera, radar, and the LiDAR. We design different strategies. These different strategies considers the working mechanism and also the data structure, the data character of all these sensors. Yeah. So we believe this way that this is the best way to achieve a reliable test. Okay, so here are some results of the evaluation part. We can output some evaluation table, some evaluation report, or some result figure here. And on the right side, we showed a real case of the radar evaluation. So here you can see from this figure, it shows three very common problems of radar detection. So here is the over-segmentation. Right? The right box is the ground truth data. There is a vehicle here, and the radar output two targets here. So it's an over-segmentation. Here for this one, it's false negative. Actually, there is one vehicle here, but no result from the radar. For this one is the position deviation. So actually you can see this car is leaving the highway and the position of the radar shows a very big error here. So actually all these problems can be detected using the reference system. And also it can help the operator to find these problems, the over-segmentation, false negative, false positive, position deviation, misclassifications. All these problems can be found by the reference system. Okay, so next part I would like to introduce some extended application of the reference system. So from all the discussion today, actually we can see what is the core function or core ability of this reference system. Actually, it's the reference system can generate the large amount of ground truth data on open roads very efficiently and very accurately. This is a core ability of this reference system. And based on this ability, actually we can do many things. The first thing we can do is the perception system evaluation. I have introduced a lot about this part. And also we can do is to generate many labeled data. Also we can build an AD scenario library. Also we can use all this data as the input of a simulation software. So first about the perception system evaluation. Here is a short conclusion. So what we can do, we can do the sensor evaluation. So for LiDAR, radar, and camera, we can evaluate the performance of each sensor itself. Also, we can do some system evaluation. For example, ADAS system evaluation, we can just test the, say, ACC, AEB, LKA, all these functions. Yeah. And here, the next user case is about the label data generation. So nowadays, people are using deep learning as the main algorithm to do all these perception jobs. So deep learning is a data-driven method. So people who have more data have more advantages. So here, this reference system actually can help to generate large labeling data, right? Here's the visualization of this. The left part, the raw data, and after the process of this reference system, you can generate all these labeled data. Yeah. And the next part is we can build our autonomous driving scenario library with this reference system. So the first, this system is a multi-sensor fusion platform, and it can do the target auto labeling, and it can it has a semantic label function. Also, it provides a big data management platform. All these functions help us to build our own autonomous driving scenario library. We can just collect a large amount of different scenario data, and this is very helpful for the product development. Okay, so the last user case is the data source of simulation. So right now, simulation are becoming more and more important in the test. People use this to test their as a low-cost solution for their perception software and algorithm. So right now, the traffic flow are generated by some softwares or some algorithms in the simulation algorithm. Here, if we use a reference system, actually we can transfer all these ground truth data into the simulation software. So as a traffic flow data. So now this traffic flow data will be very real. It's just the real world data. And in this way, we believe we can perform we can obtain a more reliable test result from this simulation test. Here just shows this workflow, the real world. We got the ground truth data with this reference system, and then input them into the simulation software. Okay, so this is about our reference system. So the next part, I would like to introduce a little bit of our company, RoboSense. Our company was founded in August 2014, and we believe LiDAR is not only an information collector. We would like to provide the smart LiDAR sensor system. And our headquarters is located in Shenzhen, China, and we also have some research institutes in Silicon Valley and in Stuttgart. So here is the development of our history. So first, our company was founded in 2014, and in 2017, we started the mass production of our R/LiDAR 16. And then we provide more products. Say here the R/LiDAR 32, the MIND LiDAR, and the Beeper LiDAR, and the Ruby 128 channel LiDAR. So we believe LiDAR is the most promising sensor in the era of AI. So here we provide LiDARs for different applications, for the robots, the robotaxi, and for the mapping, and on the like say V2X, all these parts. Yeah. So we believe that, so we want to provide the software and the hardware together to our customer. So here we provide some best LiDAR hardware, and also we provide the software with it, and together we will build some solutions. So here is solutions for the medium and low speed AD, for the robotaxi, for the V2X, and here is the reference system I introduced today. Okay, so this is everything I want to share today. And if you have any questions, please contact us with the email or some other media. And thank you all.